Okay, so is there any query related to the previous discussions which we have already had previously? Okay, so in today's lecture, we are going to discuss about uh, the entire LiDAR system characteristics that include the specific properties of LiDAR, like multiple returns, how we can select a laser, okay? What are the fundamental concepts of bathymetric LiDAR? And then after that, these are the specific components related to the LiDAR system characteristics, okay? Then after that, we'll talk about LiDAR, airborne LiDAR operation. Like before any airborne survey, what we need to do, what are the first step, okay? So there is the first step is flight planning. So certain parameters are first decided before flying an aircraft to collect laser scanning data, okay? Then in airborne LiDAR processing, the next step is once you have the data, okay? So there are standard set of data processing, okay? So those briefly, those data processing steps we'll discuss. And then finally, we have already gone through the advantages and applications of LiDAR, okay? So we'll move to the next step. That is how the sensors collected by how the individual sensor data is combined together to geolocate a laser footprint. Okay. So in the basic principle of laser scanning, specifically in case of airborne LiDAR. So in the previous discussion, we have seen that like in case of terrestrial laser scanning, okay, this LiDAR instrument is mounted on a tripod, okay, and a local coordinate system is defined with respect to laser scanner unit. Fine. So what happens once you initialize the instrument in case of tripod mounted LiDAR? Okay. So that instrument is continuously firing the laser beams and they are distributed in the space by horizontal and vertical rotation. So they cover the area in its own field of view and points coordinate are collected in its own coordinate system. It's laser, the instrument coordinate system. Later on, we discuss about what happens when we install this LiDAR instrument on the moving platform like aircraft, vehicle. Like in this case, you can see that this laser scanning is being performed using airborne platform. Okay. So aircraft on board LiDAR instrument is mounted. And as you can see that the red lines are showing the direction of laser beams which are hitting on the ground. Okay. So once you initialize the system, entire system, it continuously fires the laser beam in a particular field of view. So if you see the downward, actually this PPT, I can't I can't make a note on this. So I will select a separate file there. I can discuss additionally in addition with this discussion. So as you can see that from left to right, in a particular field of view, laser beams are confined. Okay. And the rotation is provided by internal rotating mechanism that we have seen previously. Like there is an internal mirror, there is a laser source continuously fire the laser beam. That laser beam hit the mirror and made mirror direct that laser beam in a particular field of view. Okay. So in that field of view, the laser beams are confined and they hit the ground point. Okay. And further that aircraft is moving forward, then the continuous beams which are fired from the laser source, they are hitting the ground and they are covering the area of interest in a strip. Okay. And as you see that the 600 meter is a width of strip that is covered along the flight direction. Okay. And this 60 meter is the distance covered by the aircraft in 1 second. So it is determined on the basis of flying speed. So 60 meter is covered in 1 second, and the pulse firing rate of the LiDAR instrument is 100 kilohertz. So in 1 second, 100 kilohertz laser beams are fired, and in the same time, the 60-meter distance is covered by the aircraft. Okay. So overall, how many parameters we have? We are just analyzing over here. That is speed of aircraft, how it is moving forward. Then the LiDAR instrument, it's how many pulses are fired in 1 second. And then finally, when these pulses are hitting the ground, what is the width of the swath? Okay. What is the width of the strip that is covered along the flight line direction? So let's say so at a particular point, let's say aircraft is somewhere here. So this is the flying aircraft, and over a terrain this aircraft is flying. It is moving forward at a speed of v. We can say it's v meter per second. Okay. Now what happens, as we have discussed before, if I plot over here, if I draw a schematic in this block, I'm drawing a schematic how the laser beam is diverted. So let's say somewhere we have this, this is the laser source that continuously fire the laser beam. Okay. And somewhere here, we have the rotating mirror. Okay. So this mirror rotates if this way. Okay. So if you see this architecture of how this mirror rotate in the vertical direction, so that rotation mechanism restrict the firing of the confinement of laser beam, which are fired downward within a particular angle theta. And with this theta is called as FOV, field of view. Okay, we'll see the role of theta. Now, let's say the first laser beam is fired, then vehicle move forward. What happened? In a slant direction, second beam, again vehicle moves forward, third beam, like, and many footprints we have in between these, this first footprint and last footprint, we can say. Okay, so in one scan line, if I say this is a scan line, this is called as so in one scan line, the first laser footprint and last laser footprint, and within these two footprint, all other laser beams are fired. What happened after that? Again, there are two types of rotating mirror, oscillating, and there are two types of this. We can say the movement. Okay, there are two mechanisms through which this there is an angular motion provided to the mirror. It is rotating mirror or oscillating mirror. And this is the mirror unit. Okay, so the way it moves, the angular this angular motion provided to this mirror, it is either rotating or it is oscillating. If it is rotating. What happens after this? Again, in the second line, this will be the first laser footprint, and we'll have the last laser footprint. And in between, we have a footprint of remaining laser beams. So if we see over here, theta is a total field of view within which all the laser beams are confined. This platform is moving at a speed of v. There is one more parameter, this laser source that I talk about over here. This laser source, if I talk about pulse laser, this pulsed laser system. So we have already derived that the pulse laser system continuously fire the laser beam as a pulse. Okay. So one pulse is fired, there is a gap. Second laser pulse is fired, there is gap. Third laser pulse is fired, there is gap. Fine. And this is a periodic signal. So in this fashion, this laser source is firing the laser beam. That laser beam is hitting the mirror. So there is a reflection takes place. It's a mirror. So Snell's law apply over here. Angle of incidence is equal to angle of reflection. So once this normal changes, if you provide the angular rotation, the normal of this surface changes. And that is responsible for the providing the different direction to the laser beam, like in which direction laser beam is fired. And so that the theta, that is field of view, is covered. Okay. So the rate at which this laser beam is fired as a pulse laser is called as pulse firing rate. So PFR stands for pulse firing rate. Fine. So we have derived over here. We have analyzed over here the LiDAR system characteristics into the parameters like FOV, speed, and pulse firing rate. Okay, these parameters are responsible for getting how dense the laser footprints are on the ground. If you increase the density of laser footprints per unit area, it means we are collecting more detailed coordinate information that we'll see. Okay, let me go back to the previous slide. Okay, so we have seen that how the laser beams are fired. Okay, and what are the role of speed, what are the role of pulse firing rate, why within only theta angle all the laser beams are confined. So these three parameters ultimately determine how dense the laser footprints are, okay, from the ground. So that is a basic mechanism through which laser scanning is performed using airborne platform. Now the second thing, it's again done to the airborne platform, bathymetric LiDAR. Okay. So bathymetric LiDAR is used for the water bodies study, geometrical study. As you see in the figure, uh, laser beam is fired, it hit the water surface. Okay. So if we see that there is a air to liquid medium. So when laser beam enters from air to liquid, at the interface that we call the water surface, we'll get one reflected echo. Further, the remaining amount of energy is penetrate inside the water and reaches to the water bed. Okay. From the water bottom, we have a second reflection. And as you can see in the plot of reflectance versus time, there is two return and there are two local minima. Fine. So the green color peak is from the water bed and the blue color peak is from the water surface. So as we have discussed previously, the laser beam which is generated from the laser source is generally in near infrared band. Okay. And here we are using that system for the bathymetric application. Is it feasible to have a kind of two reflection from the water, one surface and another from the bottom using NIR band, laser beam fired in NIR band? Anyone can participate in this discussion. Can we do it using NIR band? Shivam, could you please unmute?
Yes, sir.
I hope you have understood the query.
No, sir.
Hmm?
Sir, repeat कर दीजिए, please.
Please mute. Sumit.
Yes, sir. Sir,
Hmm.
there is one thing like water absorption band, sir. I'm not exactly remembering that value, sir. That does it lies between that particular water absorption band or not? That is why I'm not able to answer that particular answer. If it will not be in the water
If
absorption,
you fine, if you recall the spectral signatures that we have we discussed in the remote sensing lecture.
yes, sir.
So there is a transition of there is a transfer of energy from air to liquid. Is it?
Yes, sir.
So what is the spectral signature of water in NIR band?
Sir,
Do we
not
get enough in near infrared band? Do we get enough reflectance from the water?
No, sir.
no, no, sir, because sir, actually, sir, the NIR band lies from the 0.7 to 1.3 micrometer. So maybe
Yeah,
because of
correct.
that.
That is correct. 0.7 to 1.3 micrometer is NIR band. Correct. So do we get enough reflectance from water in NIR band? If you see the spectral signature of water,
No, sir. No, sir.
okay, please mute. Uh, Arun, could you please unmute?
Yes, sir.
Yeah. Would you like to respond this query?
Sir, as we know that the reflectance we get from the water is not enough just because of the NIR band zero point 0.7 something to some.
Okay. So all of you, please see it very carefully. So in the remote sensing course, we have already seen that how water respond to the incident energy. Okay, so the laser beam is also kind of incident energy. So the response of a material is plotted in terms of reflectance versus wavelength. Okay, and the reflectance is equal to this reflected energy component. It's a ratio between reflected energy component divided by incident energy. Fine. So if you see this water, if I say this is 0.34, and this wavelength is in micrometer. Somewhere, let's say we have 1.3. Okay. Till 0.7, it means I'm just confining within the visible spectrum. So visible spectrum, where eyes can see the object, that is 0.4 to 0.7 micrometer. Okay. So within the visible spectrum, it's 0.4 to 0.7. Okay. So within the visible spectrum, water has reflectance. Okay. And after that, this rho is equal to nearly equal to 0 if it is a clear water. Okay. And the wavelength generally that is used in laser scanning is, let's say, 1.4 micrometer. So it is in NIR band, near infrared band. What happens when at lambda 1.4 micrometer, rho is equal to 0? What does this mean? The reflected energy is equal to 0. Okay. But I have discussed that we get a return from top, we can get a return from the bottom. How it can happen? For that reason, what you need to do for bathymetric application only, you need to decrease this wavelength to be in infrared band. Sorry, to be in visible spectrum. Okay, so lambda is selected to the laser source. Lambda is generated in the visible spectrum for the bathymetric application so that we can get a reflectance from the water surface as well. It should not be completely absorbed by the water, so that one reflectance we get from the water surface and another reflectance we get from the water bed. So there is one specific property that has to be discussed over here in the context of bathymetric applications. This is the water surface, water bed. This laser beams is false, and one reflected energy will get. Let's say this is a transmitted beam. So one reflected echo will get from here. It can further travel. Okay. The remaining, after the reflection, the energy will decrease. So remaining part further travel inside, and from the bed we get a second return. Okay. So if we plot how the response in terms of like the reflected energy and reflected energy from water surface, reflected energy from water bed, as well as the transmitted energy from the transmitter. So this transmitter transmit this energy. Okay. Then point P1, this is point P2. At point P1, we have a reflected component. Okay. Then again, the second component we have, though this is less, the second one, because the second component we have from the point P2. Okay. Now point P1 and P2, and let's say this is the origin of laser source. And this origin of laser source is also considered as the origin of internal coordinate system of the instrument. Okay. So actually, this is the reference point from where we calculated distance. We'll see how these two returns are further processed, what kind of derived parameters are computed. I hope now it is clear to you, all of you, why we do not use an IR band for the bathymetric application. Why we decrease wavelength so that it is in visible spectrum. Reason is that, very clear, the water has a reflectance only in the visible spectrum. So in an IR band, there is no reflectance. What will be the problem when we don't have a reflectance? Can anyone tell me, like, let's say a beam is fired and it is completely absorbed. So why we can't calculate the coordinate of that point?
Sir, because it will not receive at the receiver end.
Correct. What happened?
So corresponding to that, sir, we don't get any DN values. No?
No. See, there is no role of DN value. Okay, I think I should repeat that part once again. Okay. All of you, please see very carefully. I may ask you one by one after that, after explaining this concept. So the process I have already explained. Okay, how the point that is hit by the laser beam, how that point coordinate is calculated. Again, I'm going to repeat that process. This is the aperture of laser transmitter. Okay. And we can say that this is the laser source. Okay. And we have an integrated counter circuit as well. Laser source and counter circuit. The role of counter circuit is to count the time. Please remember, the counter circuit is used to count the time. Time elapsed in a process that is counted by the counter circuit. Okay. When a laser beam just leaves the laser transmitter, this is the shape of laser pulse with respect to time. This is a peak amplitude AP. Okay. When this laser beam just leaves the laser transmitter, a trigger signal is generated. Let's see. We call it trigger signal. Okay. This trigger signal trigger the counter. Yes, now you can start counting. So this trigger signal initialize the counter to start the counting. So let's say that is time t1 at which this trigger signal is generated, and this t1 time is it is stored in the counter circuit. Okay, this is the initial time from where this counter circuit is starting the counting of time. Okay. Now this laser beam that emanates from the laser source travels in the medium. Here we consider particle nature of this is light source. Laser beam is generated from a light source. So considering dual nature of light, we consider it, though quanta of energy is responsible for this shape. Okay, so we consider particle nature of light. Okay, so when we consider particle nature of light, we can say that this beam is traveling in a straight line. Fine. Now, please. Let's say this is the water surface. This is I can say the 90-degree rotated view. First interaction takes place over here. Okay. And there is a laser beam generated. This point P1. This travels in a straight line. This laser beam is generated over here. Okay. And further, this laser beam travels to this end, backside. Again, in a straight line, follow, traverse the same path. And this is the location of laser beam when it is received at the receiver. Okay, so we can say that these are the receiver signal. So this shape P1 is generated from here. So corresponding to point P1 when this signal is received at the receiver. Okay, so let's say somewhere here I am plotting this. This is a receiver antenna. This receiving the signal. And again, when the signal is received, this receiver is generated a second trigger signal to the counter. Okay, now stop the counting. So this is the first trigger signal. Stop the counting. Then TS again. This is second. Stop. Stop the counting. So at time T2, the counting is stopped. So this difference of T2 and T1 is recorded from the counter circuit. This is the main role. This is the first information. We can say this is the raw information that is recorded in the counter circuit. What happens if we don't have a return, if we don't have a signal like this? Okay, so if we don't have, then receiver is not receiving any signal. There is no generation of counter. This is trigger signal, and there is no stop mechanism. So this is the reason why the T2 will not be calculated. So when we don't have enough return like this, okay, so counter will not generate, receiver unit is not generate second trigger signal to stop the counting so that time T2 is recorded. So this is the reason why the enough amplitude should be there in the return signal. If it is very weak and less than the sensitivity of the receiver, then the trigger signal will not be generated. Fine. So just see over here, this is this plot over here is a giving time T2. at time t2, okay, this shape of this echo is received at the receiver, and at time t1, the trigger signal, it is transmitted by the generated by the laser source through the transmitter. So using this timing diagram, we can calculate t2 minus t1. It is, let's say, t21. So this time t21 is actually the total time taken by a laser pulse from laser transmitter to source P1, then back to the laser receiver. And it travels in a straight line. Just see. It travels in a straight line. It means T21 can be divided by 2 to get time taken in one way. And we'll call it T, time of flight. Okay. Alok, could you please unmute?
Yes, sir.
Now I hope it is clear to you. We are not dealing with pixels over here. Fine.
Okay, sir.
So this total time of flight is recorded. Fine. And if you multiply it, speed of light in the medium air, then you will get what you will get. What it will be? Who
So
will tell me?
distance from the sensor.
Distance
Range of
from
the
the
target.
The range of the target, if you see this schematic over here, from where to where? In this case, I'm talking about this first pulse at P1. And for that pulse, this calculation is done. Time of flight into speed of light in the medium. क्या होगा? What it will be for the P1?
So distance of water surface.
From where?
So from the sensor.
From laser source.
From origin O. Okay.
Okay, sir.
So it is the distance. It's a we have selected this origin O at the optic center of this mirror. So this is a distance D and OP1. Fine. Distance O P1 is calculated. So distance DOP1 is calculated first. Now this second pulse P2. Now we'll see. When this is received, trigger signal is generated, counter stop the counting. Again, we have the second pulse. Okay. So this counter circuit has a mechanism to identify the multiple returns. Okay. So again, for the second pulse, that is from the point P2, this counter, it counter generator second time. Let's say it is T3. Okay. And what is the time difference between T1 and T3? Oh, sorry, this the transmitted pulse and the second it return, that is from the water bed. The second we have from where? It is from point P2. So we have a T3 minus T1, and that is equal to T31 corresponding to point P2. So can I write it? The range, the distance DOP2 is equal to T31 into V. If I take it, is equal to C. Is it correct? Tell me, is it correct? The distance from O to water bed, the point lies at water bed P2. So distance from the origin O, P2 is equal to Time difference between transmitted laser pulse to the return from waterbed T31 into speed of light. That I'm taking C. Sumit.
No, sir, that it is there will be some difference in velocity because there is a difference in variation, density variation between water and air.
Yeah, correct. So see, medium changes. O to P1 is air medium, while P1 to P3 is medium is liquid. So we have to split it. And how it can be done? We need to measure this difference as well. Okay, that is difference between T21. So the DOP2 will be equal to, just see, it will be equal to DOP1 plus DP1P2. Fine. And DP1P2, DOP1 we have already calculated, DP1P2, that is depth of the water. Okay, this P1 P2 is calculated using this distance. Again, you need to divide it by 2, so that this is equal to T21 divided by 2 into speed of light into the water. Fine. Because this, see, when this pulse is, why I have taken divide by 2? When this pulse is reflected back, I mean at a first interaction, when we have a reflected echo, this original pulse is traveling from P1 to P2, again traveling back from P2 to P1. So the total this gap between P1 and P2 is equal to 2 travel. I mean the time taken in a P1 to P2 and back to P1. So this is the reason why the T2, sorry, this is D32 hoga. Because the T3 we have at P2. Okay. So the time T32 divided by 2, and here speed of light. So let's see the benefit. Like when we have a 2 interaction, first at water surface and second at a water bed, we can estimate the depth of water using this bathymetric LiDAR principle. Okay, this is an exclusive application of LiDAR. It can penetrate, it goes into the water, it hit the water bed, return back, and we can able to measure the depth of water as well by recording 2 different echoes from the corresponding to the transmitted laser beam, like this laser beam. Okay. Now the third characteristic, it's I can say this second characteristic, multiple return mode. So as I have discussed before, the LiDAR sensor, this receiver unit has capability to sense the multiple return corresponding to one transmitted laser pulse. And as you can see over here, when that laser beam goes through the tree canopy, okay, just see the first return we have at the first interaction point, then this beam can penetrate into the tree canopy, second interaction, third, fourth, finally, the laser beam is very narrow. Okay, it can penetrate to the leaves of the tree and it can go to the water. This go to the ground under the canopy. So last return we have from the ground. And the instrument is timed pick up signal at a certain interval. So the receiver unit is sensitive to pick the signal at the certain interval. That is, I'm talking about the return signal. Okay. And the property of multiple return is the first pulse is used to survey top of the object, while last pulse is used to survey the ground below that. And it can clearly shown over here the shape of the return that we get to the tree canopy. Just see the various interaction points where we are getting the return. So this return signal is processed at the receiver and the local maxima. The time the receiver device pick the time at the local maxima. That local maxima actually characterize the return. So in this case, we have a 5 return. First return generally we consider it can be from top of the object, while the last return can be from the ground. Now the most important part is how we select laser. And if I go back to the discussion, over here, okay, the first discussion, that is these parameters we select, and second discussion like how the laser beam is generated as a pulse laser from laser source. It finally hit the target, and what we actually measure is the distance from origin O to point P1. So I'm talking about over here the point P1. How we characterize a point? How to define a point? Who will tell me?
Sir, any particle which is long enough to interact with the wavelength of the radiation, which will
No,
give the
no.
reflect.
Geometric definition of a point. Any surface, if I say this is the point, how you characterize it? How mathematically it can be characterized?
Any feature with having area 0.
Correct. So let's say we have a footprint. If we have a circular area, okay, with radii r, so area will be pi r square. Fine. When we say the point is defined as a geometrical feature which is having a delta that is equal to area A limit A tends to 0, you can say. Okay. So any geometrical unit that is having area tends to 0, close to 0, that is defined as a point. We are measuring coordinate of a point. Continuously, I'm talking about point P1, point P2, etc. Okay. It means we are interested in measurement of coordinate. This if origin O and P1 I am talking about. So this distance we calculated DOP1. Okay. So this DOP1 means point O and point P1, distance between 2 points. Can the laser ensure that when it hit the target point P1, the entire energy is confined within this area A tends to 0? Is it the case? If it is not, how it can be obtained? What should be the property of laser through which we can obtain? Okay, because see what is happening, as you have seen over here, this case over here. So here I'm telling that the transmitter has aperture. This is antenna. This has aperture. It has size A. We call A transmitter. Okay, and this transmitter is generating a laser pulse which is having enough energy. That high power laser pulse should be generated. Because if it's not high power, this is time t. Okay, this is peak amplitude AP. So the high power laser pulse should be generated. Okay, and there is a direct relationship between the power within a laser pulse to the area of transmitter, this aperture size. You can't decrease this because see what happened. when this surface starts emanating the laser pulse, so it is confined within this. Let's say this is a cylindrical confinement, no deviation in the medium. Okay. And finally, it is hitting the ground within the same area AT, that is transmitter aperture area. But generally, it is not the case. There is a dispersion, diffraction occurs in the medium, and this beam disperses. And again, we have a dispersed beam, and it hit the ground, and at the footprint means energy that is scattered around the target point P1. This area is, let's say this is the radius R. So this radius R is greater than the radii of transmitter. But what we actually want, this footprint area, let's say if I talk, this area is characterized as AF, that is footprint area. This AF tends to 0, so that all the energy will converge at a point P1. Actually, this we want. This is the situation that actually we want to, to obtain this situation, we want to design a system. So what should be the criteria to select a laser beam such that this condition can be satisfied? Or we are very close to this condition, AF tends to 0. Okay, so these are the list of criteria which we use while selecting the laser. Okay, the first one is high power laser. As I've discussed before, the maximum peak amplitude AB should be sufficient so that high power can be generated. If it is not high power, what happens? From the low reflecting material, the return that will get, that is very weak. And there might be possibility it is less than the sensitivity of receiver. So in the return signal, very less energy, very less power signal will be received if at the receiver. And if it is below to the receiver sensitivity, that trigger signal can't be generated. So this is the reason why we need to have a high power laser beam. The second one is short pulse length. I will discuss about that. The laser pulse I am talking about in one of the previous lectures. I have already discussed about how to characterize a laser pulse. So the pulse length is TP. That is from 50% at the rising edge to the 50% at the falling edge. High collimation, just see. The laser beam should be highly collimated so that we can obtain very small laser footprint. Here I am talking about that AF tends to 0 condition. Again, narrow optical spectrum so that the effect of noise can be reduced. Narrow optical spectrum is, as we have seen in the remote sensing, we sense a pixel, a ground area element, using a spectral band that is having a bandwidth. Okay, if we talk about red band, so it is having a bandwidth. While in case of laser, we want to generate laser beam at one fixed wavelength, not a spectrum, not a kind of like this is a spectral band which is having a bandwidth. So bandwidth we are trying to keep tends to 0. So at one wavelength we consider to generate a laser beam. Further, the wavelength is selected in a spectral in a particular wavelength where it is having a it satisfies the eye safety requirement. Okay. In visible band, for the general understanding, in the visible band the laser generated is not eye safe. So this is the reason why for the topographic application we select a laser in near infrared band. Okay. Now the wavelength at which laser is selected, at that particular wavelength, there should be the enough reflectance from the most of the materials from the Earth's surface. Like we have already seen in case of water. In case of water, if we select in NIR band, we don't get the reflectance. But if we talk about most of the topographic features from the land, not from the water, in NIR band, most of the features have enough reflectance. So it is fine for the topographic application of the land area, terrain, okay, where water is not present. So NIR band, the beam selected in NIR band is sufficient. Okay. So spectral reflectivity of laser from terrain features are considered. These 6 parameters are very crucial while selecting the laser. And for the detailed understanding, I will again elaborate the concept one by one. Like why we requirement narrow band, this narrow pulse length, why we want to make it highly collimated, why we select only one wavelength. Okay, due to some technical reason, I disconnected. Till where you have connected with me, because I shared my screen, so I could not see this application. Hello.
The selection of laser points we heard, sir.
Fine. So the
Some kind.
6 points that I have discussed, it is clear to you. You all of you heard about that.
Yes, sir.
Yes,
Fine.
sir.
Okay. Fine. Good. So there is 5-minute break. We'll again start the detailed discussion on those 6 points. Okay. So I ask you to kindly once again just see the discussion we had, and if there would be query from that will also be taken up in the next session. That will be continued after 5 minutes. Okay, so do you have any query related to the previous discussion? Okay, so the first point is that beams should be highly collimated and at a fixed wavelength. How high collimation can be obtained? Just we can see. And what is the meaning of high collimation? Okay. So the high collimation, it means that laser beam should be pointed wherever it hit. This is somewhere in the center we have point P1. Okay. This is the area footprint. And we consider it should be tends to 0. How we can obtain tends to 0? We call it highly collimated pointed laser beam. Okay. So this is the laser transmitter. This transmitter has aperture AT, the size area through which the laser beam is generated. Okay. What happened? To obtain AF tends to 0, if we consider the ideal case, I hope the screen is clearly visible to you and I'm audible.
Yes, sir.
Yes, sir.
Okay. Okay, good. So AT. So to obtain the requirement that we want to make it AT tends to 0, but we can't do this. Why? We have also defined that the generated laser beam should be high powered laser beam. Okay. So high powered laser beam means this amplitude AP, the beam is generated with respect to time. The 50%, that is 0.5 AP. Okay. This gives us the TP, that is pulse width. And what I told that this TP should be very narrow. Narrow means we can say the short pulse length. We also call it TP's pulse length. Why it is pulse length, I will just explain it. Short pulse length. In ideal case, that it should be pulse. It should be an impulse signal. If it would be an impulse signal, it is best. But we know that any electronics, using any electronic circuit, we can't generate an impulse signal. Okay. And even we can't generate an exact square shape pulse. Okay. How we generate? We generate a Gaussian shape pulse. In ideal case, it should be impulse, but we can't obtain it. But we want to make it TP very narrow. I will explain why it is so. And this TP is pulse length. Now, this area T tends to 0, but from a point, if this aperture becomes point, we can't generate a high power laser beam. And this is the requirement. So high power laser beam can't be generated. So we should have a fixed AT. It means this is the confinement. We can't further decrease this. So when within this confinement, this laser pulse progresses, this is energy within this confinement. At least this will be the AF. What happened next? That this is not actual confinement. Please wait. When this laser beam passes through the medium, so medium is not ideal. Okay. There is a diffraction in the medium, and due to which this beam is deviated. And this will be the footprint that we obtain. So due to the high power requirement, we can't decrease 80. This is fixed. This level of collimation, we can't further decrease this. It is decided because we need a high power laser beam. Now the second is this angle alpha. Okay, so there is angle alpha. Let's say this is alpha by 2, and again this is alpha by 2. Okay, so this is a diffraction angle. So this diffraction angle alpha is measured as 2.44 lambda by dt. dt is the diameter of transmitter. So diameter is transmitter is dt, and this is a monochromatic wave. This is a monochromatic laser beam, we call it. It means it is generated at a fixed wavelength. So that is a lambda value. Now just see what should be the alpha. Alpha should be 0. If it will be 0, then only we can shrink these. Ultimately, we want AF tends to 0, but AF now it is equal to 80 if medium is ideal. But we have a component alpha that is responsible for deviation. So how we can further ensure this? Because in that case, this AF is greater than 80. Okay, and how much greater than 80 depend on the value alpha. This alpha tends to 0. How it can be obtained? Either by decreasing this lambda, or increase the dt. Okay, so dt we have already decided based on the power requirement. It is fixed. We are not going to change dt. This has been already decided on the basis of how much power we need to generate. So we have only one option to decrease alpha is to decrease lambda. It means lambda at NIR band and lambda at, let's say, red band, lambda at green band. Out of these four, which will be the best? In which case we have a list alpha, alpha NIR, alpha red, or alpha green. Yes, Vardhan, could you please unmute?
Alpha green will.
Please wait. Yes, Vardhan.
Yes, sir.
Yeah, tell me.
Sir, in green band we have higher wavelength, so alpha will be less.
Green band, high
Sir,
wavelength. The relation between alpha and lambda is linear.
yes, sir.
Alpha is directly proportional to the wavelength. So if you
Yes, sir.
increase it, then alpha will increase. No, why you are talking?
Sir.
Alpha green and alpha NIR, which one is highest? Sorry, this lambda green, wavelength at green band and wavelength at NIR band, which one is highest?
So wavelength at NIR. Sir,
Correct.
lambda. Yes, sir.
Okay, NIR is at the higher wavelength, no?
Yes,
And
sir.
green, and below that we have a red, and least wavelength we have in green.
Yes,
Okay,
sir.
so lambda green is a least one. So when at a lambda green we have a lowest alpha, and in that case we have a least area of the laser footprint, and that is desirable. Fine.
Yes, sir.
But again, please mute. Again, we need to consider the eye safety issue over here. And that we have seen that at a shorter wavelength, the laser intensity is high and it is not eye safe. So there is a trade-off, and finally we select lambda at NIR for the topographic mapping. So it is decided, lambda at NIR is decided. At that we have, let's say, alpha NIR. Okay, and now we have a size of laser footprint. Okay, now the second part is, what do you mean by short pulse length, as I discussed before? No? So just see, this is the laser beam, laser pulse transmitted. Okay, this is a point at which it originate. Sorry, this is point at which it originate from the transmitter surface, and at this point it leaves the surface. Okay, and this beam is confined within this conical. Now just see the shape of this. It's a conical confinement, 3D conical structure within which laser beam progresses towards target point P1. So this is, let's say, this is time, let's say T1, and this is T2. This distance is called as pulse length. Generally, we define a 50% label TP. So TP multiplied by, if it is air medium, C. This is called as length of this pulse in the air when it travels towards the target. So this length should be narrow. Okay, narrow in such a way, as I said before, we want it actually impulse. Like in this case, TP is 0, no pulse length, TP tends to 0. And this actually we want. Okay. Why we want that? Further that I would like to explain it. So is there any query in this discussion? किसी को कोई confusion है तो बताओ. Because now I'm going to discuss about why this short pulse length is required. I hope this concept is clear to you, how the laser transmitter laser pulse, and one trigger signal is generated. And when it is received at the receiver, the second trigger signal is generated and time is recorded, total time of flight. Same process and same description I use over here to understand the concept why the short pulse length is required. Okay. Laser source, it is generating a laser pulse. Okay. We have a counter circuit and a trigger signal is generated. See, problem is that, like, this is a rising edge, then peak is obtained, we have a falling edge. And again, let's say this is a pulse with TP. Okay. Let's say if TP generally we consider 10 nanosecond. So 10 nanosecond, what is a pulse length? Who will tell me? If this pulse is moving at a speed of light, then the pulse length D, let's say we can, that is 10 into 10 minus 9, speed of light 10 to the power 8. Sorry, this is 3. It's a 3 meter. See, very large distance, 3 meter. Pulse length itself 3 meter. If there will be error, 1 nanosecond error will be responsible for error in 30 centimeter. And if there is error in 10 nanosecond, just see there is error in 3 meter in the range. Very precise electronics are required. Even very precise clocks are required. What happened? This is the rising edge, 50% peak. Now we have falling edge, 50% and int. At which level the counter trigger signals will be generated? Because see, the pulse starts leaving from this point and end at this point, and length covered is 3 meter. So question is that when this pulse is leaving the laser transmitter, this at which particular signal label the trigger should be generated. This is 3 meter. This pulse has a many over this pulse there are many time point. Okay, where the trigger signal is generated to counter to start the counting. If we make it, if we compress it, all these points to one line, then there is no problem. When this impulse is released from the transmitter, at the same point trigger signal is generated. But impulse we can't generate. But one implementation we can do, the TP should be very less. This is the reason why we call narrow beam. 10 nanosecond is sufficient. And we select a point either at a rising edge or falling edge. This will be discussed later on. Like how the counter record the timing, what are the mechanism we adopt to generate to trigger the counter. Okay, but for general understanding, while selecting a laser pulse, we need to select a pulse which has TP very less, narrow. And 10 second is generally acceptable. So I hope it is also clear to you. Now we'll see how to calculate area of laser footprint. I hope you are also making a note on this, as I suggested before. Praveen, could you please unmute?
Yes, sir.
Are you making note as well?
A little bit. Some
How you can recall later on? Can you recall it? It is fine. But I suggest even if you are not making it right now, you are just listening. That is fine. But whatever discussion we are having, please after the class sit for half an hour and make a note on that, because this discussion is not available in any book.
Yes, sir.
Okay.
Yes,
So it is advised to have a kind of note. If you can't make it while the lecture, that is fine, but I suggest you to write it after the class.
Okay.
Because later on, if you will go to search the book and try to see these things, so you will not get it there.
Okay, sir.
Fine. It is for all of you, not only for Praveen. It's a general suggestion. Okay. Okay. So second thing, how we calculate the laser footprint area. Okay. Fine. So let's say if we have a point, just consider is 80 tends to 0. It is point, and this is the location of optics origin O. Due to angle alpha, let me. This is angle alpha. This is a range. Source O to point some point P1. Somewhere this point P1 is lying. Okay. First we calculate this DF footprint diameter. So how it can be? This is, let's say, range R. It is given. It is calculated. This is angle alpha by 2. Okay. This is point P1, A and B. Tan alpha by 2. So tan alpha by 2 is equal to this length, that is d p1b divided by p1o p1 distance, that is r. Okay, so this d p1b is equal to 2 times, sorry, it is equal to r tan alpha by 2. And we know that distance A and B, that is equal to diameter DF, is equal to 2 times d p1b, because this distance is equal to this distance. There is a symmetry, no? These two triangles are similar, this triangle and this triangle. So DAB is equal to DF, which is 2 times this. Ultimately, DF is calculated in this case. DF is calculated to r tan alpha by. It is clear to all? When we have considered our aperture as a pointed source, in that case, there is area is tends to 0. And due to diffraction in the medium, the beam is deviated, and finally the footprint DF is 2r tan alpha by 2. Is it clear to all of you? Is there any doubt? Vibham, could you please unmute?
Yes, sir.
Is it clear now?
Yes, sir, it is clear.
Okay, good. So, but it is not a case. It is not tends to 0. We have a definite area. So what will happen? It will be added over here, and further we'll have a this symmetry will be there. This will be over there. So what we need to do? Just we need to add this. Let's say this is diameter dt. Dt is a transmitter diameter. So df, now the df will be 2r tan alpha by 2 plus dt. So this is the diameter. And area can be calculated. It's pi by 4 dt. Df square will be the area of footprint. So just see. This is the objective function. What we want df tends to 0. We need to optimize it. So we need to have what should be the flying height. If you want to keep df small, the flying height r should be less. You need to fly very closer. Then again, alpha, tan alpha, if you see, the alpha should be less. The dt, again, this dt should be less. Okay, so this is an objective function that you want to minimize. So if you decrease r, then there is a another compromise in terms of, like, we'll see it. If you decrease the r, then you require more time to map the area. Okay. So the summary of the discussion that we have today is multiple return, how a laser beam, particular laser beam can hit the multiple target and multiple returns are sensed. The laser has this property only. Then after that, we have discussed about what are the parameters like speed of platform, field of view, pulse firing rate. We have talked about bathymetric LiDAR, how the depth of water can be calculated. And then after that, we have discussed about what are the key characteristics of the laser that should be considered. Okay. So this is all about the part of today's discussion. If you have still any query, now that query can be taken up further discussion. I'm leaving this screen as it is so that once again you can go through this. And if you want to make note on this, you can note it. You can make a note on that, how to calculate a diameter DF. And again, you need to see this pulse length TP. The pulse length is TP into C. And TP I'm considering over here, the pulse length, this pulse width, 50%, this one. So let me know when you are, you complete your note on this so that
Hello, sir.
hello.
Sir, why we are adding aperture diameter of aperture in DF?
It is very simple. Try to think. See the geometry, just plot it and just see. Okay, let me explain. If this is the transmitter, if medium is ideal, same will be the size of laser footprint. Okay. If medium is not ideal, then again we'll have, and this will be the size. This length plus this length. It is A, B. Okay. This length is actually we have calculated. This is alpha by 2. This is radii r. And this length will be equal to, let's say this is A dash and this is B dash. So D A dash is equal to 2 r tan alpha by 2. These two triangles are symmetrical. So B dash B will be also equal to, this is equal to D BB dash. So DAA dash plus D, this will be the length of this segment plus this segment. And it is equal to 2r tan alpha by 2. Area tends to 0. When you make it tends to 0, it will be tends to 0. This will be the actual this shape, the first one. Okay. Now what is remaining? This is dt. So add this one as well. Is it clear now?
Yes, sir.
Good. Okay. Any other query? Any, if you think that there is any small, very, I mean, small confusion as well, that can be discussed. No issue. That has to be discussed. Everything should be clear to you.
Which length we are?
Yeah, you are not audible.
Which length? Sir, am I audible now?
Yeah, clearly. Say.
Which length we are taking it as R?
R, it can be, no, it can be taken this range. Flying altitude can be taken.
Okay, sir.
Because see the range vary now. If we see that from if terrain vary, the range vary. So generally flying altitude is taken as a range to do this calculation. This at what flight now from the ground the aircraft is flying, and that flight altitude value is given by the GPS. We have seen that now this when from the moving platform we have GPS plus IMU that gives a trajectory. Then we have a 2D laser scanner unit. So GPS gives the coordinate of this flying platform. Even we have a discussion on this, like if you see that, if you want to analyze the actual footprint with respect to the range means that is measured by the sensor system itself. If this is target point P1 and then range is measured, and we want to analyze what is the footprint corresponding to that range. So at a off Nadir location, if you see, though this is a part of further lectures, but even I would like to just highlight this. There will be distortion. Let's say somewhere here, your sensor system is okay, and it is firing the laser beam. Don't confuse, this is slant direction, this is terrain. Okay. And this is the nadir, just below it. So just below it, we have a shape of, let's say, circular. But when it is slant, in that case, what will happen? The shape will be distorted. This range increase. So what happened? This range increase, this will become elliptical. Okay. And even that size, we can say this is footprint site AF is more than the footprint site of AF from at Nadir location. Why it occurs? Due to the larger range covered from the laser source to the target point. Because I have seen that now the AF, you can see it is a function of how many parameters? Function of alpha, function of range, and what else? Function of diffraction angle alpha. Sorry, I have already included it. Function of transmitter diameter, that is 80. And again, this alpha is further function of lambda as well as transmitter diameter dt. Better to write it not 80, not area, but rather than dt. Okay, so overall, if you see the AF, the area of laser footprint is a function of wavelength, function of transmitter diameter dt, range from laser source to target point P1, and what else? 3 parameters. Okay, if you see while the operation, the variable parameter, which one is a variable parameter out of these 3? Lambda, dt, and what is third parameter? That is R. While the laser scanning operation, which parameter varies? Lambda is a property of laser source, it is fixed, it is not going to be changed. dt is a fixed architecture of laser transmitter, it is not changed. Only variable is range R. AF will be only affected by range R. Okay, so this is AF become a dynamic parameter and it varies with respect to range from the point to the laser source. So if there is no query, then we can stop our discussion over here. Okay, thank you. We'll continue from the next lecture.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thanks, sir.
Thank you, sir.